This model. In this model, let us have an insight of Introduction to Microwave Systems and Antennas. That is from Antenna and Microwave Engineering for 7th semester ECE. So at the end of this session, the student will be able to apply the basic principles and evaluate antenna parameters and link power budget. Actually, the microwaves are the form of electromagnetic radiation whose frequencies ranges between 300 MHz to 300 GHz, and their wavelengths are from 1 meter to 1 millimeter. So different sources define the different frequency ranges as microwaves, and this definition includes both UHF and EHF bands. The figure shows the spectrum of the electromagnetic waves. Here the waves are radio waves, microwaves and infrared and visible light, and then ultraviolet rays and X-rays and gamma rays. And the microwave frequency bands, as I said earlier, the wavelength ranges from 1 millimeter to 1 meter, and their frequency ranges from 300 GHz to 300 MHz. Their photon energy varies from 1.24 milli-electron volt to 1.24 microelectron volt. So these are the different microwave frequency bands. That is, for L band, their frequency ranges from 1 to 2 GHz, and whereas for S band it is 2 to 4 GHz. And C band varies from 4 to 8 GHz, which is mainly used in satellite communication. And KU band ranges from 12 to 18 GHz. And in this table, you can see the various microwave frequency bands and their frequency range and wavelength range. Now, let us see the physical concept of radiation. When electric charges undergo acceleration, then electromagnetic radiations will be produced. And for this radiation, we need a motion of charge, that is currents. And not all the current distributions will produce radiation. Only certain particular current variations will produce radiation. So to create radiation, there must be time varying current, that is di by dt, and acceleration is required. And if the charge is not moving, a current is not created, and there won't be any radiation. So if the charge is moving with a uniform velocity, and if the wire is straight, then there won't be any radiation. But if the wire is curved, then an infinite radiations will be there for a curved and discontinuous terminated bend. And if the charge is oscillating in a time motion, it radiates even if the wire is straight. And this is shown in this figure. So figure shows the various forms of radiations, that is when the current distribution on the antennas which produces radiation. Usually this current distributions are excited by transmission lines and waveguides. And the basic principle of radiation is, it is based on the Maxwell equation, which predicts the radiation of EM energy. While transmission lines are designed to minimize the radiation loss, the radiation into free space becomes the main purpose in the case of antennas. So the radiated power is proportional to the square of IL or QV, that is IL the whole square or QV the square, where I is the time changing current in amps per second, and L is the length of the current element, and Q is the charge in coulombs, and V is the time charging velocity. Now let us see how a transmitting antenna radiates power. The transmission line is connected to a source generator at one end, and along the uniform part of the line, energy is guided to the plane TEM with little loss. The spacing between line is small as a fraction of lambda. And as the line is opened out and the separation between the two lines become comparable to lambda, then it acts as an antenna, and it launches a free space wave, sine wave, and to the transmission line flow out of the antenna, but the fields associated with them will be keep on going. And from this view, we can say that there is a resistance called radiation resistance, which appears at the antenna, that you can see in this figure. So this is the radiation part and transmission mode. And now let us see how radiation is received in a receiving antenna. Actually, the active radiation by other antenna or passive radiation from distant object raises the apparent temperature of aura. And this has nothing to do with the physical temperature of the antenna itself, but it is related to the temperature of distant objects that the antenna is looking at. So RR may be thought of as a virtual resistance that doesn't exist physically, but is a quantity coupling the antenna to distant regions of space via virtual transmission line. And this figure shows the antenna in the reception mode. Now let us see the near and far field regions. When a signal from a transmitter is applied to an antenna, it radiates the electromagnetic waves, as I said earlier. So this electromagnetic field characteristics can be varied as a function of distance. So they are divided into main two regions. One is near field region and far field region. The near field region is defined by the equation which is less than 2d squared by lambda, where d is the maximum linear dimension of the antenna and lambda is the wavelength of the EM wave. And the near field is further divided into two parts, and reactive near field. And reactive near field is the field where the distance lies below 0.62 into square root of d squared by lambda. So this in this region, the E field and H field will be 90 degree out of phase with each other and therefore reactive. And the second type of near field region is radiative near field, and this region is also known as fractional region. In this region, the range, the distance varies between 0.62 square root of d squared by lambda to 2d squared by lambda. And the next region is far field region, which comes after the radiative near field. This far field region is also called Fraunhofer region, and in this field the E and H fields are orthogonal to each other and to the direction of the propagation of the plane waves. So in the far field region, it is greater than 2d squared by lambda.